So, welcome back. Hi, everyone. Um, let's proceed with a rather technical talk of interference attacks on ultra wide band technology provided by Mr. Wu and Mr. Yang, both from China. Um, Mr. Wu focusing on wireless security. He holds a bachelor's degree in optoelectronics and a master's degree in electronic engineering of the University of Surrey in UK. And Mr. Young focusing on embedded systems. He conducts pen testing on vehicle parts, does research on Internet of Vehicles, and holds multiple patents. He has a master's degree in computer science and of the University of Electronic Science and Technology of China. Mr. Wu, Mr. Yang, the stage is yours.
All right, thank you. Welcome to our talk today. We will talk about interference attacks on UWB ranging for IEEE 802.15.4z standard. I am Zhongjie Wu, and you can see here my colleague, Mr. Yuqiao Yang. We are from GoGoByte. Okay, so a quick introduction of our company. GoGoByte is a hacker-driven company who believes one cannot defend without knowing how to attack. We are founded in 2020 by a team of researchers and white-hat hackers from top-notch security companies, automotive product security teams. GoGoByte team has experience both in blue team and the red team. We know how to attack and defend. Our team members have shared researches at security conferences like Hack in the Box and Black Hat and DEF CON, etc. They have published security books on automotive security, on hardware security, and on wireless security. We are also deeply engaged with security communities like ASRG, GoGoHack, DEF CON, because we think the contribution by hacker communities is very important. Of course, as a company, we aim to bridge the gap between automotive and the security industry by providing automotive industry with one-stop comprehensive security solution to help the automotive industry tackle security challenges from concept phase throughout development phase to decommission phase of the products. Here are some of our team members. Okay, why and how do we design our product? Well, GoGoByte team members have been helping many OEMs and suppliers to patch security vulnerabilities. During the process, we identified a few challenges that needed to be addressed and come up with corresponding solutions. First of all, design flaws. Automotive cybersecurity vulnerabilities discovered at operation phase are hard or expensive and even impossible to fix due to design flaws because the lack of risk control and patch management capabilities planned from design phase. We provide Defense Weaver to help the auto industry with secure by design. The second challenge is insecure implementation. Many vulnerabilities we found are not because there are no security consideration during design phase, but they were because of insecure implementation by developers during development phase. It clearly showed the lack of comprehensive security test and validation capabilities. We provide GoGoBark to help auto industry with security test and validation. Today's talk is about one test case of GoGoBark. Okay, the third challenge is slow and inefficient security response. We reported vulnerabilities to vendors, some of which took only 1 month to push an over-the-air update to fix it, but some others took a year or more without actionable plans to fix it. We provide Threat Hound, an automotive threat intelligence platform, to help identify threats in time. And finally, we have Threat Trace, the all-in-one automotive security platform to tackle these challenges. The one platform that helps tackle all aforementioned challenges. We integrate all these applications into one platform and enable the orchestration of applications and personnel inside and outside. It is a common industry consensus that cybersecurity vulnerabilities cannot be eradicated, before operation phase due to the complexity of automotive systems. So the agility of a security response is a key performance factor of a vendor's security capabilities. Okay, here is a brief content of our talk today. We will introduce the background on UWB technology, and then we will show the principles of our attack. Next, we will play a demo video, and finally, we will talk about some mitigations and have a Q&A session. So a brief background on UWB. The ultra-wideband technology has seen wide adoption in the past years. Numerous players in the field of connected vehicles have invested heavily in UWB, including the automakers such as Audi, BMW, NIO, and Zeekr. Also, semiconductor vendors and ECU suppliers such as NXP, Qorvo, Apple, and Bosch, among others. The CCC also adopted UWB technology for the digital key specification 3.0. Here we can see a screenshot on the BMW press release site. We can see that it announced the new digital key with ultra-wideband technology. Here is another screenshot from the Audi Media Center, also featuring the ultra-wideband technology. And here, a screenshot from NIO's website. You can see on the right of the screen that they are featuring the UWB digital key and the UWB smart key. And here is the screenshot on the Car Connectivity Consortium, or CCC's official website. This is about the digital key release 3.0. We can see they highlight UWB multiple times in the highlights section. So why does ultra-wideband find such extensive use in car keys? Well, we use it to counter relay attacks against the traditional PKES systems. The traditional systems use RSSI, or received signal strength, to estimate distance. The signal strength can be spoofed using relay attacks. Traditional PKES using LFRFID or Bluetooth or NFC are known to be vulnerable to relay attacks. Ultra-wideband has, by definition, enormous bandwidth and sub-nanosecond pulse width. So the endpoint communicating with ultra-wideband can measure time of flight with nanosecond precision, thus determining range with centimeter precision. We can also transmit data over the ultra-wideband channel, achieving what we call simultaneous measurement and communication. Because of its enormous bandwidth, ultra-wideband is inherently immune to narrowband interference emitted by traditional RF systems. This provides higher reliability in complex RF environments, let's say in densely populated areas or in underground garages. Here is a brief overview of the changes to the IEEE 802.15.4 standard over time. Notice in the right of the page, we have IEEE 802.15.4z in 2020. They added an STS sequence to enhance the security of ultra-wideband communication. Also note that there are two modes of ranging, namely high-rate pulse repetition and low-rate pulse repetition. We will go into details shortly after. So in this slide, we show some scenarios for relay attacks on the traditional PKES systems. Two attackers carry with them two relay devices, one of which approaches the targeted device and the targeted vehicle, and the other one approaches the key fob. Then the PKES signals are relayed back and forth between the vehicle and the key fob. The relay devices, because they are close to the car and the key, they will produce strong received signal strengths on the car and the key, thus making the car and the key believe they are close to each other. This type of relay attack has been demonstrated to be effective against PKES systems using low-frequency RFID or Bluetooth or NFC. When attackers mount a relay attack, they don't care about what data is being transmitted. All they need to do is to relay data back and forth quickly enough. So cryptography alone is of no help here. By combining time-of-flight measurement and cryptographically secure messages, in theory, ultra-wideband is able to perform secure distance bounding. It looks like UWB is the ultimate solution to the PKES system. This is apparently widely accepted by the industry. We noticed Mr. Ohun Suzer mentioning the low attack feasibility of UWB. But our question is it really? Now, the latest standard introduces two ranging modes for ultra-wideband, as we mentioned earlier, the LRP and the HRP mode. The low-rate pulse repetition employs fewer but stronger pulses. We consider this mode to be secure. The high-rate pulse repetition mode will use numerous but weaker pulses. We consider this mode to be potentially vulnerable. Okay, here is an illustration of the two modes of operation, namely single-sided two-way ranging and double-sided two-way ranging. The ultra-wideband message contains timestamps, as we see colored in black here. So the receiving endpoint can determine the time of flight by comparing the timestamp and the time at which the packet is actually received. The clocks are not synchronized accurate enough at the beginning between the car and the key. So in single-sided two-way ranging procedure, two packets are transmitted, first from the initiator to the responder, and then from the responder to the initiator. In this case, only the initiator has knowledge of the distance. For the double-sided two-way ranging, one extra packet is sent by the initiator to the responder. Thus, the double-sided two-way ranging procedure will give both endpoints knowledge of their distances. The STS sequence added by 802.15.4z standard can be seen in the diagram colored in yellow. When using UWB in secure ranging, the STS is usually negotiated out of band using cryptography, acting kind of like the shared secret in Diffie-Hellman key exchange. The receiver determines the time of reception by correlating the STS signal versus a local template. Because the
Sometimes it's like this. We experience technical issues. Mr. Young, do you mind to share maybe your screen if you have it open and proceed maybe explain the next slides? And you're on mute. And if Mr. Wu is sitting somewhere close, maybe he can just join your room. Ah, super solution. You're still on mute?
sorry for the interruption. I think we have a network issue.
That's fine. You solved it permanently.
Usually, the STS sequence is negotiated out of band using cryptography, and the ranging is done by correlating it with a local template. Because the STS is negotiated securely, a third sniffing endpoint can neither accurately estimate the time of arrival, nor can they forge a valid packet, assuming the STS is only used once. Okay, here is the operation principle of a UWB receiver. When the receiver powers on, it would start acquiring signals over the air. In the process, it will correlate the signal with a local template of the preamble, trying to find the preamble. When the resulting channel impulse response exceeds some predefined threshold, then the receiver would proceed to look for the STS. When the STS is also found in the same manner, then the receiver would continue processing the packet. When in either case, the threshold is not exceeded, like for example, the preamble is not found, or the or the STS sequence is not found, then the receiver will drop the packet. To attack this receiving sequence, we can deliberately corrupt either the preamble or the STS, such that the channel impulse response will never exceed the receiver's threshold. The packet would then be dropped. The UWB ranging procedure would eventually reach a timeout and fail. So how can we implement this attack? As we can see in this slide, we have these 4 packet formats. We can send a malicious SP3 packet with incorrect preamble and STS, but with higher power. This will interfere with the original packet, and 2 possible outcomes exist. First, the receiver's input amplifier would get saturated and cannot receive correctly. Second, the 2 packets would collide in time, and the receiver will fail to correlate the preamble or the STS, thus dropping the packet. Well, we have a problem. UWB signals are mostly transmitted at frequencies well above 6 GHz. The time domain pulses are extremely short, and the transmission rate is extremely high. Therefore, even if the attacking device sends the malicious packets continuously, there is still large intervals between the time domain pulses. Thus, it is almost impossible to interfere with the ranging packets. So, how do we find the right time to attack? My colleague Yuqiao will explain in detail.
Okay. The good news is that we can use the double-sided or single-sided two-way ranging sequence to find the right time to attack. We will use the double-sided as an example here. By the way, we create a attack device called GoGoBark, whose feature I will describe in detail later. In conjunction with the double-sided two-way ranging sequence, our attack device GoGoBark first records the timestamp of receiving message 1 by using this timestamp as a reference and applying appropriate delays. After the delay, we send out our attack packet. About how to adjust the delay, here's how we did it. Before the attack, we first sniff UWB ranging sequence packets, records the timestamp reserved to each packet. With this data, we can probably estimate a delay and then further adjustment in the real attack process. At last, we need to adjust this delay to match the time when the receiver receives the correct packet. We have an interesting name for this whole process called UWB, UWB accurate defining. Based on the above ideas, we sum up 2 strategies of attack. The first strategy is in spatial domain. If GoGoBark is set to attack the initiator, it should be close to the initiator. In time domain, it should choose to snipe message 2 packets, adjusting delay to interfering with message 2 packets. Similarly, the second strategy in spatial domain, if GoGoBark is set to attack the responder, it should be close to the responder. In time domain, it's supposed to snipe message 3 packets and adjusting the delay to interfering with message 3. Okay, let's talk about our attack device, GoGoBark. First of all, we choose Curva's DW3210 chip as the UWB chip because it supports IEEE 802.15.4z high-rate Porsche standard. Many car digital keys, such as XP, Apple, all support this standard. The second, we finished the UWB packet sniffing and sniping function on GoGoBark. For the sniffing function, I refer to the GitHub project produced by Alexander Harrocks. We had a friendly email exchange. We can use GoGoBark to capture packets, record the timestamp of each received packet, and finish passing the MAC layer of the UWB. For the sniping function, we used both of the previously described attack strategies, either initiator or responder. GoGoBark can perform sniping. Besides, to achieve better interference, we used the DW3210 chip and an amplifier for power amplification. Okay, finally, it was time for the real demo. Although we are successful execute the attack on a real car, because of some confidentiality reasons, we could not use the customer's product as demonstration. So we choose the iPhone 14 and the AirTag as the platform and used the attack device, GoGoBark, to attack the UWB region process. The iPhone 14, as mentioned above, also supports the IEEE 802.15.4z high-rate push standard, as do many car keys. So our demonstration can be applied to other conditions by changing just a few parameters. Once GoGoBark is getting run off, the UWB-based ranging function of the iPhone fails with a success rate of 99%. We have recorded a video in advance. Let's watch the video.
We will use iPhone 14 and AirTag to demonstrate the attacks against UWB ranging applications. And we will use our automotive security test device GoGoBark as the attacking device. For the normal UWB ranging application scenario, the iPhone will display the accurate distance measurement. And direction arrow indicator. For our first attack scenario, let's try to attack the AirTag. I will place our attacking device, GoGoBark, at about more than 1 meter away from the AirTag. AirTag, GoGoBark. As a result, iPhone cannot locate the AirTag. When we turn off the GoGoBark, the iPhone can locate the AirTag again. Okay, here we go. Let's try another attack scenario. Let's try to attack the iPhone. I will place the GoGoBark nearby the iPhone. The iPhone won't be able to locate the AirTag. And when we turn off the GoGoBark, the iPhone returns to normal, and it works again, right away. The final attack scenario is if we start the attack after the distance measurement has begun. The iPhone will only display the distance measurement before the attack. As we move farther away, the iPhone will only display the distance bar, but no longer display the real-time distance and arrow indicator. If we turn off the GoGoBark and it works right away again, GoGoBark supports UWB attack, relay attack against LF, BLE, NFC technologies, and other automotive attack vectors.
Okay. In the beginning, using UWB has the purpose of countering relay attacks. But what's happened to the whole system when the ranging function of UWB is blocked. Let's consider the following assumptions. If the car's PKE system doesn't use UWB positioning, it goes back to the traditional mode and is vulnerable to relay attacks. There's nothing to say. If car PKE system using UWB and relies on real-time UWB data, when the UWB's ranging function is blocked, the system will be unable to receive the distance data. As a result, the system will get freeze and not function at all, which is a bad outcome. If the system can use previously stored UWB data for positioning, then like the iPhone thought AirTag is linked to it in the video, the car relying on the UWB data left over from before the tag will also incorrectly assume that the car keys are nearby, and thus it remains vulnerable to relay attacks. More seriously, if the car is set to lock automatically once the user leaves with the key, then the actor can mode the tag once the key stops, and the car will not lock automatically and leads to car shifter. In short, only by issuing the normal operation of UWB ranging can it not lead to the bad results, such as stalls or stolen cars. Okay, it's not enough to only adhere to the IEEE 802.15.4z and CCC digital key standards. We propose the following countermeasures. The first, we can try to identify the high-power signals. However, this increases the complication of the receiving device and may lead to a reduction in functionality. This may not be feasible for devices with strict time constraints and portable. The second is random delay ranging. I will describe in the next page. Okay, take the example for double-sided two-way ranging, which we have modified. First, the responder records the timestamp of message 1 received from the initiator, and then sends message 2 after a random delay of several hundred picoseconds. In this way, the attack device cannot estimate the delay, thereby defending against such interference. However, it's uncertain whether this method can conform to the CCC standard. There are some of our standards, but I think the security application of UWB needs more discussion. Okay, next we can answer some questions. 我要结束先。
So, thanks for the presentation, for the clear description of the problem and some mitigation measures. We have indeed some. However, I would like to ask the first question. That's one of the privileges you have as a host. Where can I buy one of those devices just to check on one of my least favorite neighbors?
Well, if you
Is it can I actually buy it or not?
It is still under development, and I think we will notify everyone on our official website once it is complete.
Okay, so let's keep in touch, just in case. Okay, let's move on to the questions from the attendees, and I will just refresh the votes. They have been provided already. So to the attendees, if you want to upvote your favorite question, go for it, or add another question. In the meantime, I will ask the very first question. I will show it directly on stage. So the question is, your attack is focused on denial of service. What would be the advantage for an attacker compared to a high power wideband jamming? white noise, or an attacker cutting the wires of the UWB antenna, which is in some cases might be accessible on the car.
Well, on that, sorry, I just needed to switch my earphones over. First of all, if we use a high-power wideband jamming or white noise, it will almost certainly be against the local regulatory of radio waves, and it will probably draw attention by from a lot of people, because if you actually do ultra-wideband jamming, then you will be using about 1 gigahertz of the spectrum and with very high power, and you will be interfering with a lot of people's devices. So it will get noticed very soon. And also, because if you want to do wideband jamming, you have to keep the spectral power density very high. Otherwise, you will not be able to cover the actual UWB signal, because the UWB functions as very short but very high power pulses. So if you want to cover over the pulses, you will have to flood the entire spectrum with very high power, and it is most probably not very feasible. Well, about the attacker cutting wires of the UWB antenna, well, first of all, you will have to get access to the car, and then you have to, and then you can find the wires leading to UWB antenna. So it is kind of a chicken and egg problem at this point. And also, if the vehicle is designed such that you can reach the wires without any modification to the car, I think it is the car's vendor's problem, not ours.
And I don't want to be a joyless cybersecurity professional, but it sounds like cutting wires is rather sabotage instead of a hack. However, I marked this question answered. Next one. Let me just briefly filter for it. What is the maximum GoGoBark operating distance?
Oh, 这两个它
If you are talking about the operating distance between the GoGoByte itself and the target device, I think the maximum distance we ever tried is like half a meter. Yeah.
yes,
Half a meter.
1 meter, more than 1 meter.
Yeah, the longest time, the longest we have achieved is about 1 meter, sometimes even more than that.
但是它这个操作可以是
Understand, that's a clear answer. The next would be, is GoGoBark tool open source?
Unfortunately, it is not open source yet, because as I mentioned earlier, it is still under development. And when we release this tool, we will consider to put it open source.
Gotcha. Why do you consider HRP secure against your GoGoBark device?
Well, referring to our slide, LRP is based on less but more powerful pulses, and as of right now, we have not tried to attack LRP. But in theory, because the pulses are higher power, it should be more difficult to interfere with those pulses with limited transmit power of our device.
The next one is it possible to lower the measured distance so the iPhone shows distance near instead of distance far?
这个程度非常的低，4%。
Yeah, it is very low probable. We did observe that, but according to both our own research and results published on GitHub and such, it is about 4% success rate. So very low probability.
Gotcha. So we have some questions from different people, but since we have a little bit of time, I would also answer them or show them on stage. Let's see. Have you observed any variations in the success rate of the sniper jamming attack under different conditions or different UWB-enabled devices in your research?
Successful rate of the sniper jamming attack. I think yes, because we have been experimenting with a real car, as we mentioned, but unfortunately we cannot reveal more detail about that because it's a client's project. And about the we also tried that against the iPhone and the AirTag, and apparently, yeah, we do observe variations in success rates of the jamming attack and yeah, the success rate on the iPhone is higher than the car, I think.
Yes, yes.
Yeah, because I guess the car vendors have implemented some countermeasures of our attacks in their system.
Gotcha. Then there's, of course, more need for additional information. So the question is, did you publish a paper about this attack, or maybe do you plan to publish a paper on this attack?
对，我们可以将会在那个
Yeah, sure. My colleague has already finished about half of the writing, and I think everyone will see the paper this year, maybe
Yes,
maybe
this year.
this year. Yeah.
You hear that? That's a promise. Pinky promise. So, answered. Let me check for another one. What would be the impact when the iPhone and AirTag are quite close to each other, a few inches apart, and the GoGoBark tool is a meter away from these two?
Yeah, on that, because the GoGoBark works by injecting a packet and try to corrupt the legal or the legitimate ranging packet. If the two target devices are already close to each other, like a few inches apart, and the GoGoBark tool is further away from them than the distance between them, well, we cannot exceed the speed of light. So the interference will not work, and the ranging will function as normal.
I understand. So it's the physics again.
Yeah.
Okay.
Basically.
Then this question seems to be interesting too. If the authentication key fob starts the authentication procedure only in response to a dedicated key process on the key fob, then for the attack execution, you also need to enforce the victim to push the button. Is it right?
Yes, this is correct. Well, almost all the relay attacks that we have tried, they are only of practical value if we can press some button on the car and have the signals go back and forth, and then have them authenticate to each other. If only if the user have to press the button on the key fob and then the car will like unlock or lock and sort of things, then basically we cannot do the relay attack unless we have the key fob already, or we can lure the user into pushing the button. But that should be out of the question for cybersecurity.
Gotcha. The last but not least question, and I think we already answered it, or you already answered it. It's a yes or no question. Does the attack also apply for all RP?
As of now, we would say no, because first of all, we haven't tried that, and the second, in theory, we don't think it's like that easy to interfere with high power pulses.
Perfect. Good. Then I think we answered every single question in the chat. Mr. Wu, Mr. Yang, thank you very much, and see you in the lounge. So you will be there for a few minutes. So everyone in the session, please take the chance to speak to them, to exchange contacts, and if you want to know when this device is available, that's also a good thing to interconnect. So thanks everyone. See you in the next session.
Thanks. Thank you.
Okay.